Hi, you've no doubt seen my Rigol DP832 power supply in many videos before, and there's been a few issues with this supply, and I'll have to link in those videos down below if you haven't seen them. But something funny happened with this the other day when I was shooting some of that high-speed video footage. I didn't show this because it wasn't really, I didn't really get an interesting shot out of it, but I tried to shoot some, because somebody asked for it, tried to shoot some high-speed video, 1,000 frames per second, of a relay, actually contact relay in there, actually closing and opening. And here's a shot of it, by the way. It's nothing exciting at all. But what I did is I thought, oh, okay, I'll try and put some current through this thing, like the actual contacts on here, the two contacts, and actually, or put a decent amount of power through it, and then actually see what happens when I break that power, for example, or short it out. And I didn't get anything out of that, but what happened is I think the magic smoke has escaped from my Rigol DP832. I was using channel 1 here, and I had it set for 30 volts, 3 amps, its maximum capability for this channel, i.e. 90 watts. So I was basically putting this across the contacts, and then I was using another channel to turn on the coil, and then I'd activate or deactivate the coil after I press the camera record function to see if I could, get anything interesting on the relay. But look what's happened on this thing. First of all, let's have a look at channel 2 here. I've set channel 2 to the same 30 volts, 3 amp current limit, so the maximum it's capable of. And if I switch on channel 2, it does exactly what you would expect. Bam! The output jumps straight up to 30 volts like that. I've got no load on there at all, so, at least significant digit there. And everything's hunky-dory, right? Turn it off and on. But look what happens to channel 1. I've got it set to 30 volts, 3 amps. I switch on channel 1. Wah, 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 wah. And even if I leave it for a while, it's not going to get up to 30 volts. Look, it's barely, it's not even going to make 5 volts, I don't think. There is something blowing in this thing, like the output series pass transistor is blown or something like that. If we have a very quick look at a DaveCAD drawing of a typical output on a power supply like this, and I've done this in various videos, so I won't go through it again, but basically there's what's called a series pass output transistor here. It passes, because it's in series, hence the name, it's in series between the internal supply from the transformer and the output. That's your regulation element there, so it's called a series pass transistor because it passes the current, passes the power through. And there's an error amplifier here, which then taps off a divider on the output, and then there's a reference voltage, which will be your adjustable control coming from your DAC or from a pot or whatever on your power supply, which sets your output voltage. And then this error amplifier just drives your transistor, be it a MOSFET or a BJT like this. It doesn't matter. There's various configurations. And that error amplifier is just a loop that just keeps this output voltage at a constant level, because due to op-amp action here, these two voltages will, the op-amp will do anything it needs to on the output here to keep these two voltages the same. So if you set 1 volt here, then you're going to get 1 volt here. It'll drive this transistor and do whatever, and that's how it creates regulation and regulates your output. And this series pass transistor is a really quite a low impedance. You can think of it that way. So really, that's how it gets all the current through. Okay, it wouldn't do that if it was a really low impedance. So when you switch this output on here, even if you've got no load, you expect it to instantly switch to the 30 volts there. But we're not getting it. It's just slow. This output voltage here is just starting out at 0, for example, and it's just, I don't know, slowly rising up. I don't know if it's linear or what, but it seemed to have tapered off there. And as you saw, it was only getting to like 5 volts or something like that, even though we'd set it to 30 volts. It just wasn't getting there. It was taking forever, whereas the good channel just went switch on, bam, right up to 30 volts here. So what's going on? My best educated guess would be that the series pass transistor is blown, because it's the most likely thing to blow when you're shorting the output, because that's what I was doing. I was basically shorting the output with the contacts, but hey, this is an adjustable current, lab power supply. It's supposed to do this. I had the current set to 3 amps, so if it, it should have current limited to 3 amps. And you don't expect lab power supplies to blow when you short them. You expect them to go into current limit. Everything's fine, but it blew. I'm not sure whether or not it blew when I was turning the thing on, or whether I was switching it off and getting back EMF or something. I don't know, but yeah, I reckon, educated guess is that we're blowing the output pass transistor, because there's no other thing really. I mean, it's really quite difficult to blow like your error amplifier or something like that. That's usually got decent protection. And the series pass transistor, often there'll be a diode across here as well, a back diode for some protection as well. But I don't know about the configuration of this particular supply, but obviously for it to slowly ramp up over like a minute and not even get to its set voltage, obviously there's no low impedance here. It's just leakage, trickling or something like that. So let's see if we can confirm that. The way we're going to confirm this is to use my new BK Precision 8601 DC electronic load. This is a new model. You've seen my BK Precision 8500 electronic load before. Well, BK Precision were kind enough to send me a replacement. This is their new model. It looks quite similar, but it's got now dual line vacuum fluorescent display. It's much better functionality, and the specs are improved in various ways and things like that. I might have to do a separate video actually, teardown, comparing the two and doing some comparisons and stuff like that. Anyway, very nice. So what we're going to do, okay, I've just got channel 1, which is our blow-in output, just connected here, and I have not got the load switched on, but it will sense the voltage and display it here on the terminals, okay? So this is not a load, it's like open circuit, high impedance. So let's switch it on and see if this voltage tracks this. It should. So what we're checking for here, you could use a multimeter. You don't need to use an electronic load for this, but this happens to work as a nice precision 0.05% voltmeter as well. Excellent specs on the thing. So basically we're measuring the voltage on the output just to see if it's really on the output terminals here, or whether or not the display is just displaying something ridiculous and we might be getting our 30 volts there. I don't know. Who knows? Let's test it. So let's switch it on. And look, the two are tracking. There you go. They're both tracking. So this is genuinely the voltage on the output. This power supply is definitely blowing. So just for curiosity's sake, I'm actually going to switch this off and see how quickly it drops back down. Yeah, pretty quick. That's what you'd expect a power supply to drop back down to. Okay, so, but now I'm actually going to switch on the load to see if the output transistor here can actually drive any load at all. My guess is it won't. I think it's blowing, or there's something in the pass regulation element that has blown and it can't provide output current. So we'll put a constant current load. So that's what CC is here, constant current mode. I've set it for a constant current load of 0.1 amps. So it's not high, just a very low current, 100 milliamps, bugger all. So let's switch that on. So I've now got a load on the output. Let's switch it on. What do we get? Wah! See? Doesn't even charge up now. Doesn't get to anything. And if I change the constant current on that to like even 0.01, okay, so 10 milliamps. 10 milliamps, right? It can't even drive 10 milliamps. This thing is buggered. So there you have it. I killed this thing by just shorting the output with a relay contact. That's all I did, just opening and closing it. It should have current limited at the 3 amps. I was being a bit brutal to it, but hey, lab supplies like this are supposed to survive. Shorting the output, that's the whole idea of having the current limit and the maximum spec to 3 amps. If it can't survive that, it shouldn't damn well let me set it as a constant current. So maybe I got some back EMF from the contacts opening, they arced or something, and it killed something in there. But before I did this, I just tested. I actually just had my leads like this coming out, and I just shorted the two leads together, and it worked just fine. So what I'm going to do is just do that on channel 2. I won't try and use the killer relay. I don't want to kill my other channel, but yeah, look, I'll show you. 30 volts, 3 amps, okay? Here we go. Boom. And it's gone down, but it's gone up to 3 amps. There it is. And of course the output voltage is almost zero because, it's just a little bit of drop across the leads and everything's hunky-dory, right? It can survive that just fine at current limits at the maximum 3 amps. But I effectively did just that by hooking it across these two relay contacts, turning on the coil and shorting out the contacts. That's all I did, I swear. It's a shame I don't have footage of it. Now, the unfortunate thing about this power supply is that it's a little hard to troubleshoot. You can't just open it up and then just probe around. You've got to actually take a few things apart. So, yeah, this may not be easy. But the good news is it's not too bad once you actually swing this top board open like this. You could actually just power it up and leave it open. So it'd all be a bit hairy scary, but yeah, you can actually do it. So you can actually access the bottom board down here, and you can access the top board just teetering on the brink of death here. Now, we've got, this is a 3-channel power supply, 2 30-volt ones and one 5-volt one. So I can't remember from the previous teardown which channel was what. So as always, follow the money, follow the wiring, take it from, I think it's this one. I think it does actually go up to here. So I think we could be in luck in that this top board actually does channel 1, which is rather interesting in terms of arrangement. I would have thought, you'd have your 2 big ones on the bottom. But nope, it looks like it's this one anyway. Yeah, not sure if you can see that, but you can definitely see, I can definitely see the wires in this bundle here going off to channel 1 there. So, yep, I think that's a winner. I think it's that top board. Nice. And as it turns out, I just happen to have a second board here, and you'll know the reason why if you've seen the previous video. It had to do with the fact that this previous board had a design fault that used too small a heatsink here. It got way too hot over the maximum junction temperature of the voltage regulator. Poor design, and they had to re-engineer it with this much bigger heatsink here. So I've done a separate video on that. So I just so happen to have a board, and ta-da! I should have a spare series pass transistor. You can always tell the series pass transistor, it's the one on the monster heatsink here. And if that's not a dead giveaway, then once again, follow the money. Here's the 2 big spade lugs here for the output voltage. It goes, oh, look, there's our output current sense resistor. There we go. It's just tapping off. You can see the 2, look, see the 2 traces coming out there, going off to an amplifier in there, and that will be doing the current sensing. But yeah, the 2 big traces just go off, so you can't see precisely where those traces go, but there they'll go maybe under the heatsink and in to our output series, to our series pass transistor right there. And we can just follow some traces here. Here's negative of a huge cap there, and there it is, that negative point there. So that's going to be our ground, and it's snaking its way over to there, which is, ta-da, that, the bottom lead of that resistor there, and that goes off straight to a spade lug. So that's obviously the negative output. And there's Chinese symbols there, even though the silk screen's a bit dodgy on that one. That's going to say negative in Chinese, I'm sure. And then our resistor jumps across here, and that goes to the other huge trace here. So obviously they got that directly across the output rail, so that's a bleeder resistor. So what that bleeder resistor is doing is actually discharging the output capacitor. You may have seen it in the shop before, I don't know, right down. There's actually an electrolytic capacitor, I don't know what value, maybe a couple hundred mic or something like that, directly on the output terminals, a couple hundred microfarads. So that actually just discharges that capacitor, and you saw that. You remember when we switched the power supply off, even with no load, it dropped back down to 0, and that's the bleeder resistor actually discharging that output capacitor there. But you might be thinking, well, how can they get accurate current control? Because this is like 0.05% current adjustment and stuff. If we've got a constant, basically, this resistor is going to take a reasonable amount of current on the output. Well, you'll notice that the current sense resistor is on the other side of this bleeder resistor here. So the output, it's sensing the current going out here, not through there. So this can be any value you like. And that transistor is a CEP60N15, and that's 150 volt, 30 or 60 amps, depending on the package, or even higher, N-channel MOSFET. So, you know, something typical you might find in an output power supply like this. But this could be the culprit, because MOSFETs have a downside in that they aren't nearly as robust as BJTs, bipolar junction transistors. They're almost bulletproof. You know, you put in a 2N3055 in your power supply and Bob's your uncle, right? You're never going to blow that thing. They're just robust as anything, whereas MOSFETs are pretty delicate little flowers. You know, you've got to be careful. They can be damaged by ESD or, you know, you've got to be careful with them, although they have, you know, often much superior performance characteristics. So there's advantages to using them in series pass applications like this. But yeah, I think we might have come a gutser there. I can actually see also, is that a couple of diodes down in there perhaps for protection? And just for completeness, the series pass transistor is not the only thing in the current path there. We've also got our current sense resistor that we looked at here. So just for, you know, these are usually pretty robust. It's going to be almost impossible to damage this thing except at really gross overloads. We'll just check that, double check it. Yep, it's still intact. Yeah, just as a matter of course. So there's not much that can go wrong here. As we saw this filter capacitor before, the output of that filter cap, big fat trace there. Looks like they've got another bleeder resistor on the main filter caps. That's quite nice attention to detail. Big fat trace disappearing under the heatsink. Guess where it's going? It's going to one side of the MOSFET, and of course the other side of the MOSFET comes out. So really, that's the only thing in the path, unless there's, as I said, there's some sort of, you know, control circuitry thing blowing, but I don't have the schematic for this thing, and that's the last thing that you would expect. Because when you're mucking around with this thing, shorting the output, and you know that's what you were doing, and then all of a sudden it failed like that, you know, okay, we might have popped the series pass transistor. That's best guess. So yeah, you wouldn't go mucking around, chasing red herrings down a rabbit hole here with the circuitry unless you've looked at the series pass transistor. But just as a matter of course, let's see if we're actually getting a voltage on the input to the pass transistor, the output of that capacitor that's there. So I'll just measure that. So once again, it's unlikely to be the issue, but hey, let's probe the voltage on the output of that cap just to be 100% sure that there is voltage getting to the series pass transistor, just as a matter of course. So let's switch it on, and oh, whoa, hello, it's on. The lights are on, but nobody's home. I'm making contact. Wow. Something else has blown. Like, it's not the capacitor, maybe there's a fusible element. You know, a fuse in here somewhere. It might be a PCB mount fuse that's actually blown instead of, I hope so. Because the last thing I want to do is replace the series pass transistor on the heatsink. What a pain in the butt. So, wow, there's no voltage getting to that. I haven't disconnected anything. Everything's still coming in. Oh my, like, even if I disconnected the control cables, it wouldn't have made any difference. This has nothing to do with actual control. So, wow. Yep. Gonski. I'm not on AC. No, I'm on DC. Wow, there you go. It may not be the series pass transistor. My potential apologies to the series pass transistor. Actually, I don't remember any relay. I don't see any relays in this thing. I didn't switch the output on there, but there we go. I'm switching, hey, there we go. I'm switching the output on. That's interesting. And 1.7, no. No. Okay, that's interesting, but I would have expected a voltage to be there regardless of whether or not I switched on the output. It shouldn't matter. It should always be energized. That cap should always be powered up. No, there's something definitely wrong. I don't know what's going on. Could be being back-powered somewhere. I don't know. No, it's still not right. Bingo, found the culprit. There it is. There's the fuse. Here was the input. Okay, this is the tap coming from the transformer. You can see it going off here. The big thick traces going off into the rectifier over here. And it's in series with a fuse. There it is. PCB mount fuse. 17 meg. Gonski. Now, ordinarily, you might have to take out all these screws down here. I think there's 6 or 7 of them to get the board out so you can access the bottom of the board to suck out a component like that. But in this case, we've got easy iron access to it. We just heat up the top 1 pin at a time, lift it up so we can lift the component out. No problem. I've taken it out. There it is. Gonski. And then we just apply some solder to the back to the top there. And then we get our trusty solder sucker or solder wick or whatever floats your boat. And suck it out. Oh, that lovely sound. So that we can put it straight back in. Beauty. Bloody stupid cheap ass solder suckers. It came these 3 little knobby things here, and these are supposed to go in the side there and hold the thing on. It's a bit dodgy, brother. Oh, there we go. It's supposed to lock forward, but moving it or shuffling around on the bench pushed it back. Yeah, bit dodgy, brothers. And there's our culprit. It's a little 5 amp jobby. Now, like 3 amp current limiting on the output. Okay, it's a reasonable value to expect in a design like that. But why it's blowing? I don't know. It's not like it was, inrush current from the caps or like what? Why? I don't know. Is it just a cheap ass one hung low brand that's sort of just dodgy and has failed? Or is there some more systemic design issue here in terms of, actually failing? I don't know yet. It looks like it's got all the requisite stuff on there. Look at that. UL. It's all hunky-dory. So, of course, with that board, I had a direct replacement 5 amp fuse. No worries. So I've whacked it in there. Hopefully I've connected everything back up correctly. And I'm going to turn it on. Here we go. Big test. Come on. Power up. 30 volts, 3 amps, switch on. Whoa, 39 volts. Nope. 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 Fail. It's not regulating. There's more than the fuse. Aha. And also, it's not just the voltage. Check it out. It's drawing 0.7 amps, 27 watts. Where on earth is 27 watts going? Wow, that's a lot of power. There's nothing on the output. I swear. Nothing up my sleeve. Actually, I'm kind of glad that didn't work because it's kind of a bit boring. We just popped a fuse. Whoop-de-doo. This is more interesting. And, well, I guess you could say, maybe I should have checked the series pass transistor as well. But, I was feeling lucky. Turns out I wasn't. Anyway, but my first guess is still that series pass MOSFET because it's got to be to get 39 volts or whatever it was on the output. That's probably the transformer tap here. So it's like it's shorted or something like that. Where it's drawing those 27 watts, I don't know. Okay, here we go. You can see some components heating up there. There we go. I just switched it on and yep. Let's have a squiz under there. Oh, that little heatsink there. There you go, 60 degrees. It's that little tiny one in there. It's not the pass transistor. You can see the pass transistor there. It's not getting that hot at all. It's that puppy. Interesting. And if you're curious to know the rail voltage there, the output of the rectifier and the transformer, there we go, 53 volts. It's a 63 volt cap. So that seems a bit high for a 30 volt rail, but I don't know. I can't remember if we've measured this in previous videos or not. But yeah, I don't know. It seems a bit high, but hey, it's just a transformer and a rectifier, so I'm sure it is what it is. You can really see that little heatsink there is like 97 degrees, something like that. I have not got the output switched on, by the way. Wow, so that's that little puppy in there. Woo! Now, the great thing about having a spare board like this, you can test your hypotheses. So let's have a look. I've got, it's powered on, the output is not on, and that same heatsink is only, 37 degrees or thereabouts. In fact, this little puppy next to it is a little bit hotter, so it is significantly different. But hang on, I'm not just going to jump in and take that bait. I had a look at the part number on this. This is a BD136, and a bipolar tranny, and these are pretty robust little things. Why is this getting super duper hot? Yet the main regulator here doesn't. I suspect that there's nothing actually wrong with this. It's just sinking the current that maybe the failed pass transistor here is dumping into this thing. So yeah, once again, you don't want to chase those red herrings down a rabbit hole. So let's have a look at the data sheet for this N-channel MOSFET here. And it's gate, drain, and source. Let's go between gate and drain. Here we go. So, sorry if you can't see that. Doesn't matter. 2.5 ohms. That doesn't sound very good between gate and drain. Let's go between drain and source. Look at that. Dead short between drain and source. Gate and source. There we go. Let's swap the probes around. Get a different polarity. Gate and drain again. 2.5 ohms. Yeah. Let me have a smell. Yep. Culprit. And if I get our good board, just to show you, let's go between gate and drain again. Here we go. Ta-da! Open. Exactly what you'd expect. You'd expect the gate to be open. And drain and source. There we go. 4.5K. Yep, I think something's gone horribly wrong with the pass transistor. As you'd expect, it's MOSFET, little delicate flowers they are. And, well, I don't know. Actually, hey, look at this board. You know how I showed you before that there were some diodes in there? This is the old board. No diodes in there. Look, here we go. There's the new one. They've added some diodes. I didn't notice that. So they've upgraded. Maybe protection on this board, perhaps. But maybe a fat lot of good it did. So we're at a point that there's a pretty good bet that our pass transistor here is failed. So luckily I have the spare board. I have the exact type. It's not like I'd have one of these puppies lying in my junk bin. You'd have to be really into your pass transistors to have one of those. I might have something maybe kind of sort of would work. But yeah. No, I've got the real one, so I'll just swap it. Well, hello. Look at this. I have not touched that. I just took the board out from the metal bracket there. Look at the hand solder residue on that. It's nothing. Look, here's another. Here's the other, the BD136 on the heatsink. It's properly soldered. And this one, somebody's had a go at that. Look, you can even see a scratch mark on the board from the iron, I think. What? And just to verify, we've got it out. Here we go. And nope, that is not normal for a MOSFET. The gate is supposed to be open. Nope. Gonski. So there you go, replaced. Of course, don't forget to put the heatsink compound on the back of the thing first, just a little bit, and make sure you screw it in nice and tight before you do the solder joints. And we're back in circuit, and let's do the drain and source. There we go, 4.5K, I think that's the value we were getting before, yeah. And the gate, there you go, megs, yep, good enough. Okay, so what are the odds of it working? Well, I don't know with Murphy, you never know. So everything's plugged back in correctly. Let's have a burl. And come on, you can do it. I've set it to 5 volts, I was playing around before, so let's switch on. 5 volts! Winner, winner. Let's go right up to 30. Bingo. We fixed it. It was exactly, well, I'm yet to do a load test, but it was pretty much what I thought in the first place. It was that damn series pass transistor. N-channel MOSFET, easily damaged if you don't design your product right. Clearly there's something wrong with this Rigol if we can just, blow up a series pass transistor like that. That's just crazy. And we blew the fuse, of course, so that we gave us a bit of early hope that, maybe it's just the fuse. But no, it was the pass transistor. So there you go. But it was really quite worrying that this transistor had been desoldered. You saw that. It had been hand soldered in, I'm not exactly sure why, whether or not it was a production step afterwards. It could be. That could be a normal production step. In that case, they need to use some no-flux solder or clean it up or something. But yeah, anyway, that's it. Winner, winner. Chicken dinner. What the photon is going on here? My BK Precision load is dead. I haven't even hooked it up yet. I just go to turn the power on. I swear, this is the same power cord. Look, it works. And I plug it into here. Nothing. What, bloody Murphy? Unbelievable. The damn fuse is blowing. Would you believe it? There you go, working a treat now. It was the correct rating fuse. It was 0.5 amp because you have different, because this is like a selectable voltage range on the back. You have different fuse ratings for different mains voltages, and it is, the label on the back says 0.5 amp for 240 volts, and that's what was in there, and it blew. Replaced it with a 0.5 amp, and fine. What the? These things just happen with monotonous regularity in the EEVblog lab. Is it the EEVblog curse? I don't know. Alright, let's check this puppy out. Let's switch it on. 30 volts. Let's just go, the current limit's 3 amps. Let's just go constant current 1 amp, shall we? Just for simplicity, turn it on. Yep, drawing an amp. No worries. Works a treat. So that's all it was. There's a blowing N-channel series pass transistor in there. Why? I don't know. Okay, what we're just going to do now is just do some shorts on the output. Once again, set to 3 amps, 30 volts, 3 amps, okay? Doom, there it is. Okay, it's recovered just fine. And okay, well, hey, there we go, you got some sparks. Woohoo! Beautiful, catching that? But I know what everyone's thinking. Dave, we want to see the killer relay. Try it again. Okay, this is exactly the same thing I had when I was shooting my high-speed video. Channel 1 output here, 30 volts, 3 amp maximum limit set is across the normally opened contacts here. And I've got second channel here, 12 volts hooked up to the coil. So I'm just going to switch it on and let's see. Nah. It seems to be working. Seems to be working just fine. Fine. Yep. Alright, so your guess is as good as mine as to why it died. But I swear that's all I was doing to it. And I think I did it a couple of times. I think, 3 or 4 times I got a couple of shots out of the thing. And I managed to kill channel 1. In this case, no, seems rock solid now. So there you go. I hope you enjoyed that video. It's a bit longer. I got 42 minutes worth of footage. Wow, sorry, I was hoping it'd be a quick, but yeah, in the end, it was exactly what I thought. It was the series pass transistor in there, and that BD139, my guess is it's being used to drive the gate in there, so because it's high capacitance or whatever these power transistors usually are, maybe it's used in there, and that was shunting all of that power, because the gate, as we measured it, the gate was like shorted out to the drain and source, so it was just dumping everything from the rail. How it was actually measuring it on the output, because the shunt resistor is out here for the output, but yeah, I don't know. You need the circuit or to trace it out or something. Couldn't be bothered, but there you go. Hope you enjoyed that look at this troublesome Rigol DP832. This is not the first issue we've had with it, of course. There's been a few notorious issues with it, but I thought they were done and dusted, but apparently not. I don't know, did I get unlucky? But it doesn't matter. I would not expect a lab power supply of this price and grade to blow a pass transistor in it. Why? When it was, it should current limit at 3 amps, handle it properly. I have no idea what went wrong, so maybe, Rigol, you should look into it. Anyway, if you liked it, give it a big thumbs up. Catch you next time. Thanks for watching. If you like this video, click here to watch similar ones. You can also give the video a big thumbs up by clicking down below. Don't forget to subscribe to my channel by clicking the little icon down in the corner here. You can also sign up for email notification alerts so you get notified as soon as I release a new video. No worries, that's the way to do it. You can also comment on each video down below, and all the hardcore discussions happen on the EEVblog forum. There's a separate forum thread for each video, and yes, I do read and respond to all comments where possible. And if you want to help support the channel, I accept donations on Patreon. You can buy merchandise and other things linked somewhere here. Check it out.